for
chemistry.
Yeah, baby.
Welcome to Let's Get to the Marks, going through a little walkthrough here for you A-level chemistry students. This one's on shapes, forces, ions. Let's go. So question 1, this question's about compounds that contain fluorine. Sodium fluoride contains sodium ions Na+, and fluoride ions F-. Na+ and F- have the same electronic configuration. Explain why a fluoride ion is larger than a sodium ion. So why don't you pause the video, have a go, unpause, and check the answer. Okay, what I'm doing now is I'm drawing out the electronic configuration of the both, so you can see that these ions have the same electronic configuration, and see if we can get anything from this. If we just look purely at the electronic configuration, we may have a little confusion as to why they're different sizes. We need to actually look a bit further and not look at the electronic configuration, but look at the atomic number, which gives us the number of protons. And sodium has 11 protons in the nucleus, so there's an 11 plus nuclear charge, and fluorine or fluoride ion, as it is here, has 9 protons in the nucleus, and so a 9 plus nuclear charge. Therefore, sodium has a stronger nuclear charge, has a greater attraction to those 8 outer shell electrons, and it pulls them in closer to the nucleus, hence why it's smaller. The fluoride ion, of course, has a smaller nuclear charge. Therefore, there's a weaker electrostatic force of attraction between the nucleus and the outer shell electrons, and so those electrons are able to drift away further, making the fluoride ion larger. Now, you can answer this in terms of sodium, but the question does specifically say explain why a fluoride ion is larger, so you might want to do this second sentence here as your answer. Both are worth 2 marks, but this is more the mark scheme one, which is focusing on the fluoride ion and saying, well, it has less protons, so less nuclear charge, less attraction between the nucleus and the outer shell electrons. And there we go. Let's get on to 1.2. Explain in terms of the structure and the bonding why the melting point of sodium fluoride is high. So you all know from GCSE that ionic compounds have a giant ionic structure. And if I bring up the ions again, we can see we've got the sodium ion and the fluoride ion again here. And of course, because one is positive and one is negative, there's an intermolecular force. There's a force of attraction between them. This is a strong electrostatic attraction. It's actually an intramolecular force, but there we go. Strong electrostatic forces of attraction between the positive and negative ion, or the oppositely charged ions, require lots of energy to break. Now, in a giant ionic structure, you're going to have many of these strong electrostatic forces of attraction that are known as ionic bonds, and you're going to require lots of energy to break them. Hence why it would require, well, why sodium fluoride has a very high melting point, and you don't often see salt melting when you're doing your cooking. All right, let's get on to 1.3. The ion H2F+ is formed when hydrogen fluoride gains a proton, as shown in this equation. HF plus H+ goes to H2F+. Name the type of bond formed when HF reacts with H+, a hydrogen ion. Explain how the bond is formed. So we need to name this bond and explain it. So this is known as a dative covalent bond. Oh my gosh, what have I put there? Dative covalent. Oh, whatever. Oh my gosh, covalent. Okay, we got there in the end. Dative covalent bond. You can call it a coordinate bond. It's another name for it. This is when a lone pair of electrons is donated from one atom to another atom that is able to accept a lone pair of electrons to form a covalent bond. In this situation, it's the fluoride in the H2F that is donating a pair of electrons to the positive hydrogen ion. And here's a little example of how. So this little circle is the electron from the hydrogen. It's covalently bonded to the fluorine. The fluorine has 6 other electrons, so 3 extra pairs. Guess what? It can donate one of those pairs to a little hydrogen ion, which is a proton, basically has no pairs of electrons. And that hydrogen ion will come in close, form a covalent bond where both of the electrons are coming from the fluorine and none from the hydrogen. And there we go. That's a dative covalent bond. Okay, let's check out 1.4. Fluoroantimonic, that's a crazy name. Fluoroantimonic acid contains 2 ions, SbF6- and H2F+. draw the shape of the SbF6 minus ion and the shape of the H2F plus ion. Name the shape of each ion. So this is worth 4 marks. First of all, we can look Sb here, that's the central atom here. Well, it's got 6 electrons in the outer shell. They're bonded with the fluorine atoms that are surrounding it. So there are 6 bonded pairs of electrons. And whenever you have 6 bonded pairs of electrons, you're going to get this shape, which is known as octahedral. And essentially it has a kind of square planar in the middle. So it's like got one plane with 4 atoms coming off of it. You can use dashed lines to show the atoms kind of going back into the paper, and you can use solid black lines to show them coming out of the paper, but not necessary on the mark scheme to do that, but good practice. And then we've got a fluorine atom above and one below, and this shape is known as octahedral. It's essentially 2 pyramids, or like a traditional diamond shape, or 2 pyramids with their bases connected. Now we've got H2F plus, and fluorine is the central atom here. How many electrons are in a fluorine atom? It's 7. However, it's got the positive charge, the plus, so that means it only has 6 electrons around it. How many of those electrons are bonded? 2 of the electrons are bonded with the hydrogens, so 6 minus 2 is 4. So there are 4 electrons that are on their little lonesome, and they form 2 lone pairs. So we have 2 bonding pairs and 2 lone pairs. So we've got 4 pairs around the atom, and when you have 2 bonded pairs and 2 lone pairs out of the 4 pairs, you get a bent or V-shaped molecule, just like the water molecule. So this is very similar to the shape of H2O, and so we just want to draw it like we would a water molecule. So you can see I've shown the dot on the cross here with the hydrogen for the 2 bonded pairs, and then 2 dots for the lone pairs of the fluorine. We can draw those Mickey Mouse ears if we like. I don't really need to show the bonded pair of electrons. The solid black line shows that in itself. I can show the Mickey Mouse ears or the 2 pairs of dots for the lone pairs. That's totally fine. Of course, the aim is that these pairs of electrons want to get as far away from each other as possible. They want to minimize repulsion, and we get a greater repulsion between these lone pairs, and that's why we get that bond angle with the water of like 107 or 107.5, whatever the hell that is. You don't need the bond angles here, so that's fine. But what you do need, which I nearly forgot, naughty, is to put the charges of the ions outside in brackets. Don't want to lose 2 marks for that. Okay, we're on to 1.5. Hydrogen fluoride reacts with ethyne, that's C2H2, as shown in the equation. All compounds are in the gaseous state. We've been given the bonds of CH, the triple bond, the HF bond, and the CC single bond, and the mean bond enthalpies of them. We've also been given the enthalpy change of -179. Use the data to calculate a value for the bond enthalpy of the CF, the carbon-fluorine bond in the product. Right, I like to approach these with reactants minus product equals the enthalpy change. We've been given the enthalpy change. We've been given all of the energy for the mean bonds in the reactants and all of them in the products except for the CF. So just set your equation out like this and then solve the equation. So let's start off by working out the total bond energy for the reactants. So we want the ethyne bond energy, so 412, 412, and 837. Smash that in the calculator and then add that to the coefficient here of 2 times HF. So first of all, 412, 412, and 837 equals 1661. I've now got a coefficient here. Don't forget those big numbers. You've got to multiply everything by that. So HF is 562. So I want 2 times 562. Smash those in the calculator, add them together. Oh, what do we get? We get 2785. That's the total for the reactants. So we now minus the product. So I'm going to do 4 times 12 is 1648 plus 348 equals 1996. And that equals an enthalpy change of -179. Hold on. I forgot the 2F. So yeah, we've got the missing CF bond as well. So I get 1996. That's for the 4 CH bonds. And that's for the CC bond. And then I have plus 2CF, and that equals -179. Now we need to simplify. So let's start off by taking, we want to simplify. So let's add let's take away 2785 from each side. So I can get rid of the 2785. So first of all, I'm going to minus 2785 from both sides of the equation. And what's that going to give me? Bum, bada, bum, bum, bum. Smash it in the calc. Okay, that leaves me with minus 1966 plus 2CF. And on the other side of the equation, we are going to get 2 964 minus 2964. We don't want to worry when we get our final answer about minus or plus because we're aware that the mean bond enthalpy doesn't have a sign. So now add 1996 to each side. That's going to get rid of my minus 1996. So I'm smashing that into both sides. And then I'm going to get, that gets rid of anything on the left. So I'm just left with 2 CF bonds, and they are equal to minus 968. I want to divide those by 2, and I found out what 1 CF bond is equal to. I ignore the sign, so I'm just going to leave the answer without the sign, and it's 48.
You're still here? It's over.